Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you are doing good. In this, we're going to see problem valid arrangement of pairs. Now, before even you start, I'll not tell you any jargons, any new thing whatsoever. We will build intuition from scratch. Nothing of the sort I am expecting you to know. That's it. Period. Right? Now, let's start off. It simply says that you are given a zero index 2D integer array pairs where pairs of I is start I, end I. As you can see, pairs is nothing but two values, start I, end I. An arrangement of pairs, arrangement as in some sequence, some pattern, some numbers, that is arrangement, is valid if for every index, again this entire range, that this condition satisfy. What this condition actually means? This ultimately means that end I, start I, end I, start I, end I, start I. You see what's happening? That end I of the last pair should be equal to start I of the current pair. Then I can represent it as a sequence. Now you have to return any valid arrangement or any valid sequence. The very important stuff here is the input will be generated such that there exists a valid arrangement of pairs. There will always be a valid arrangement of pairs. Now the moment I'm trying to build, obviously I will look at this specific example. I'll say okay, 5 comma 1, either the next element after it should be something which has 1 starting with it. Can I see anyone starting with 1? No. Okay, so ideally this should be some, let's say, pair. Now before it, obviously I will have to kind of place or arrange it. Before it, I should have another pair who end with 5. Is there anything? Yeah, we have. So I will put it 4 comma 5, 4 comma 5. You see, I have put up. Okay, this is kind of pair. Now for 4 comma 5, I should have another pair who ends with 4. Okay, yeah, we have. Okay, ends with 4. Then for this, I need to find another pair which ends with 9. Okay, I have 9. Oh, and then all the pairs are done. Now you might feel, Aryan, it seemed pretty simple. I would actually end up doing the same thing. I will go and get one pair, then I will check if I have some pair after it, before it, and then similarly I will keep on trying to place it, and obviously I know the answer will be there, so I will simply be able to place it. Maybe you are correct, maybe not, but the biggest issue will be when there are multiple options for you to choose from. Here, when you were at 5,1, ending at 5 was only one node, or I should say one pair. What if I have multiple pair? Then what? Okay, so that's the actual issue, that okay, if I have multiple pairs, then I have to try for every node, try for all the possible n pairs, or n, again when I say pairs, I mean these, like this is actually one pair. That's actually an issue. And again, trying this will incur you O of n square, maybe higher also. Again, if you go by via backtracking route, obviously it will be higher. If you try to optimize it, maybe put some approach there, obviously O of n square will be possible, but still that's also way more than what we demand or what we are about to do. What can we do here? Firstly, very easily we can see there's a very standard stuff here, which is a relation between some pairs. So I very easily can see that for the specific pair, I divided, okay, 5 and 1, 4 and 5. Why I'm dividing it? Because I know that this one, okay, let's say this 5 and this 5 can be attached with each other. I'm not saying they are same. I'm saying they can be attached with each other. So what I did here is that, okay, I made 11 9 as one pair. As you can see, 11 9, 11 9, 11 one node, 9 one node. So they are, again, why are it is a directed edge? This is a directed edge because the pair specifically mention 11 comma 9. It doesn't mention 9 comma 11. There's a difference between 9 comma 11 and 11 comma 9, because in this case 5 comma 1 is a pair, which means I have to look for another pair which starts with 1. Right? The same way, if it would have been 1 comma 5, then I have to look for another pair which starts with 5, not ends with 5. So the actual position 5 comma 1, 5 and 1 position matters. Thus I have placed a directed edge represent, okay, 5, 11 and 9, 11 and 9. Same way I have 9 and 4, although 9 here is a different number, but for me it is same because ideally I want to attach them. So I said, okay, 9 4. Okay, same way 4 comma 5, 4 comma 5 I have attached it, 5 comma 1, 5 comma 1. Now, oh, it seemed like a simple graph. Yeah, obviously it seemed like a simple graph. Ultimately, what's the answer? The answer is nothing but, again, giving you the actual iteration, or the iteration of this graph is the actual answer. Now you might say, Aryan, what do you mean by iteration? Iteration simply is, I can start iterating from the node 11. I can say 11 comma 9, 9 comma 4, 4 comma 5, 5 comma 1 is the answer. 11 comma 9, 9 comma 4, 4 comma 5, 5 comma 1 is the answer. Doesn't it seem pretty simple? Yes, it seems like, but there are many basic stuff which we actually missed. What is that stuff? In this case, I started iterating from 11. What if I would have started my iteration from 9? If I start my iteration from 9, then I can only traverse 9 comma 4, then 4 comma 5, then 5 comma 1. Then what? The question is, then what? You might say, Aryan, I don't know what to do with this. Probably I might start iteration from any other node which is missing, but then it will still bring you back to the condition where you will have a multiple such nodes, or multiple such nodes, because right now you just have one node. So you are pretty good. Okay, after like 9 is only having one person, which is 11, so obviously he will come. But if they are multiple, then who will you choose to place before 9? So, which makes us bring to a fact that starting node, again, considering I'm able to get this specific graph, which I should be able to easily get it, because what's happening here is I represented the pair start and end values as a node and the pair itself as an edge. And again, I didn't do consciously anything. I just thought of, let's represent them, and ultimately it became as is. Then I also realized, okay, for me, I have to ultimately tell the arrangement, which is the actual traversal. For me, it's a simply graph traversal, which we do via simple BFS, DFS and stuff. So, but for that, the starting node of this graph traversal matters. And obviously the answer will always be there. So I should not worry about that, okay, if the answer is not there or not. But the issue here is, okay, so far you're pretty good with it. What is the actual thing which you should remember, or which you should make sure that what you have done so far? You got a pair, took the node start and end from it, made an edge out of that pair, and your task is to go and iterate on these edges, which means iterate on these pairs in the defined order, and also making sure that each pair is used only once, which ultimately reflects towards this graph problem and says that iterate on this specific graph such that each edge is traversed only once. That is again simply when we converted this to a graph representation. This pair is nothing but an edge. These start and ends are nothing but the nodes. For me, I have to traverse in this. I have to traverse in this. Obviously, I will have one question of where to start from, that I might figure out by some stuff. But I want to make sure that the arrangement should follow the criteria. The criteria I have already made as a form of a graph. The only thing there is that each pair should appear only once in the sequence, which means each edge should be landed onto only once while I am traversing. Okay, so far we have pretty good idea of what we are trying to do here is. Okay, I did not put any jargons, any LXYZ stuff here. So no worries, keep on, let's go with the flow. Now, what if I told you, again, as I told you that for one node, they could have multiple other nodes, which will be around it. So how will you traverse it? For example, in this, you can easily see that for this specific array, also for this specific pairs, I made this specific graph. How will I get the answer? I know I have to go on to each edge once, because each edge represents me one specific pair, and I have to also go on to all the edges and also making sure each edge exactly once. So what I should do, imagine that right now, imagine that you start off with the node 1 as your starting node, although it's a very open question right now which node to start off from. But let's say I started off, so I traversed here, this edge is covered, this edge is covered. Again, you see, I'm not going anywhere. Then I traversed here, this edge is covered. I traversed here, this edge is covered. Then I traversed here, this edge is covered. So you see, firstly, I did not repeat any edge. I went here, then here, then here, then here, and then here. I did not repeat any edge, which means no pair was repeated. I was able to start off from the node 1 comma 2, then go to 2 comma, again when I say edge 1 comma 2, then edge 2 comma 1, then edge 1 comma 4, then edge 4 comma 1, then edge 1 comma 3. And also this will for sure satisfy because you are going on by not even putting up your pen down, which means you started from here, then here, then here, then here, and then here. You see, my pen did not even put up. So I'm going on in the order. When I say in the order, in the order, in the order I'm going, in the order I'm going, in the order I'm going. So obviously this will be the correct answer. Same way, if I take a better example, let's say this is my corresponding array. If I start off from the node 1, still it's a very big question, which node start from? But if I, because again, why it's a very big question, what if I would have started from node 3? Node 3, where I will go? Nowhere. My pen got a full stop. It's the same thing which, if you remembered in the very childhood, people used to say, okay, make the hut with the corresponding without even putting up your pen. Do you remember it? Yeah. Again, it was actually much harder. I made it somehow very fast. Maybe that's not the exact question, but tell me in the comment section what was the question what we used to solve when we were actually childrens. But if we started from the node 3, obviously that would have resulted in incorrect answer. What if I start from the node 4? Then okay, 4 1 3, incorrect answer. Then again, what if 4 1 2 5 6 7 8, then 4? Then to go on to this specific, I will have to again go on to this edge, which is repeating the edge twice. Oh, which means the starting node will matter. But right now, imagine starting node is this. I will traverse here, 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 here. Sorry, here, 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 here. Then 4, and then coming back. So you see, every edge visited once. You might have a question, Aryan, you are making us mad, like as in like you are making us crazy. Because what if you start from 1, but what if you would have gone to 3 directly? Obviously, if I would have gone to 4, then I would have come here, then here, then here, then here. It still would have worked. But what if I have started from 1 and then gone directly to 3? Then yeah, it's gonna be an issue. We'll see that also. But so far you realize, this is ultimately my maqsad is. We, from the pairs, converted to our nodes. Nodes, edges represent one pair. Just to go on to the actual arrangement is nothing but this graph itself. To go on to each pair exactly once, and also to make the arrangement, I will go on to each edge exactly once, and also will make the arrangement. Now, before you jump on to any further stuff, this thing, what thing? Traverse the graph in which you step onto each edge exactly once. This thing is Euclidean path, which is path in a graph that visits every edge exactly once. I'm not saying you should have known about it. No, not at all. People firstly tell this and then they tell the problem. That's not what I'm telling you right now. I'm just telling that if in future, if you remember this, just remember this is some word which says that if you visit every path exactly once, path in a graph that visits every edge exactly once, that is nothing but a Euclidean path. Cool? That's it. Again, just put it in the books and forget it. Coming on to the actual question. The question was which node to start off from. Because we saw that, okay, here the answer was possible, here the answer was possible. When it's possible, which means I have an arrangement and I will be able to actually make the corresponding arrangement. But if I take the same example, do I have arrangement here? Try off from yourself, start off from any node. Let's say if I start from 1, I go to 1, then 2, then 3. Oh, this never got visited. Then, okay, let's say I go on to 1, 2, 3, 4, 2. This never got visited. So, okay, in this, the answer is not there. What, again, this is simply an observation question. What made this not succeed and what made this succeed to get the arrangement? Let's see. Simply consider that you will have some sort of start node. Obviously, you will have some end node also. if you look back very carefully, for you in this question, the start node was 1. And if you remember, it was always ending at 3 when you had a correct arrangement, right? Same way, I said, okay, I will have some start node, some end node, represented by start, Sn and En. Now for this, I am referring that forget everything. Imagine that you only have two nodes, start node and end node. So they will be connected by just one edge. Forget everything else. Everything else, just forget it. Just imagine, okay, you have this. Now, just to say, okay, just to say that Sn with one edge En, this is perfectly fine. Simply two nodes, one edge, visit once, done. Now, if I just add some more edges onto Sn, I will add some more edge, which means I added a blue edge. As you can see, I added a blue edge here, but considering this blue edge also have to come back here. Now, why is that the case? It is the case because obviously in the very end, I will be iterating on this specific edge, which was the green one. So every other edge should somehow revert back to me or form a cycle, which means that this I'm making an edge now. It has to do something, do something and come back to me, so that in the very end I can iterate on this green edge. Same way I can have other edge also. Let's say red edge, do something, do something, go anywhere, come back to me, so that in the very end I can go onto that green edge. Right? I'm building the actual intuition from the very small, just having one edge. Ultimately for me, in the very end, I have to reach to that specific edge. That's what, so I'm just saying, okay, just roam around, come back to me, that's it. Which means roam around, go out, but please come back to me. Go out, but please come back to me. So that in the end, I can actually go and iterate towards my end. Same thing I can say for end also, that come, but please also go back. Come, please also go back. So if I still bring you to the very basic point, what it ultimately says? It ultimately says that Sn will have one extra out degree. En will have one extra in degree. Every other node has zero net degree, which means in degree, out degree, both are same. As you can see, every other node, it is same. Now you might say, Aryan, what if it is not? Which means I add one more edge. As you add one more edge in this, the things are disturbed completely. What I mean by that completely? See, earlier you must be traversing like right here, and then you would be coming back right here and then going to your the specific edge. Again, you could have had one more round, which means come here, then go, and then come, and then ultimately go here. This is one specific path. But the moment you have one more edge, you have to incorporate this. How will you do it? You are screwed up. You are screwed up for forever. Because of this, you will miss the corresponding other paths. Thus, you realized that for all the other edge, out degree and in degree should be same. For the starting node, the out degree minus in degree should be 1, which means I should have one extra out degree, exactly 1 I'm saying. And for the end node also, it should have one extra in degree, exactly 1. And that is, if my graph follows this, which means it will for sure have the answer. Although in this problem, they have already mentioned that you will have the answer. So we don't have to check these conditions per se. But if they would have not mentioned it, we would have checked these conditions. But still, any which ways, this line will help us to find out what should be the start node for us. Before you actually believe me and start solving the problem, make sure you go on to the questions and examples back, because everything I told you was on observation basis. Nothing I told you that you should be knowing. So observation never stops. If I look at this example, every node has in degree and out degree as same. There is no node who has a out degree more than the in degree by 1, and same way there is no end node. So Aryan, are you saying that for this node there is no start or end node? No, I'm simply saying that you can choose any node as the start or end node in this example. So I can choose 3 also, because 3 it will work, because it's ultimately a cycle. And in a cycle, any node you start off from, you will ultimately be able to reach back to that same node without doing anything. So for cycle, which means for the nodes where everyone has in degree and out degree as same, for that case your in degree and out degree can be any node, which means your start and end can be any node. For me, uh, personally, start is what I'm after, so for me start can be any node. So on top of your previous observation, you just add one more observation, that if the in degree out degree, which because ultimately you will have to maintain out degree and in degree for every node, and that, with that, if it is 1, then you will say obviously this will be a start node for me. If you cannot find any node, just assign any random node as a start node and you will be good to go. Now when I say start node, assign it, ultimately what's the maqsad like? Maqsad is to get the start node, which you will easily be able to get by simply using out degree and in degree. When you have got the start node, you know that the answer is always possible, so simply start the traversal. Now traversal as in, okay, obviously a simple BFS or a DFS traversal could work here, but why specifically DFS? Obviously we could easily see that when I was at this specific node 1, obviously now I know the start node should be 1. When I was at this node, I had option, okay, 1 2. For a specific BFS, the BFS traversal would look like 1 2. The next node it would put up as 1 4. Next node as 1 3. This is not the correct pattern. The correct pattern would be as I go on to depth wise, which means 1 2, then 2 5, then 5 6, then 6 7. So I'm going on in depth fashion. So obviously traversal needs to be there for the graph, but BFS is out of the picture. I will do DFS only. Now, is that so simple? Maybe it should have been, but if you will try and do the simple DFS, you will realize a one very basic stuff. And I'll say, highly do it and try it by yourself. What is that one thing? Obviously, now we know that we'll try the simple DFS. Let's try the simple DFS. I try the simple DFS. Okay, Aryan, start from 1. So I will have 1 2 first. Okay, 1 2 first. Again, simple DFS, as I'm going to the node. So this is my node. This is the corresponding neighbor. Simply make a pair and put it as a result. Then next edge. Obviously, I'm iterating on all the edges. So next edge is this one, because from 2 there's the only edge remaining. So next edge is this one. So this will be node, this will be neighbor. So 2 1 is next pair. Okay. Then this is visited. Next is 1 3 visited 1 3. Oh voila! The simple DFS traversal looks good. Only and only when, because you choose to start off from 1 comma 2, as in like 1, you start off to go to 2. But if you remember the same doubt I asked you in the very beginning also, 1 has a neighbor of 3 also. In DFS, you never know which node or which neighbor you are visiting first, because there is no priority in neighbors which you have given. So how will you make sure that you are not visiting 3 first? Because if you visit 1 3, 1 3 is visited, then ideally your entire stuff is on hold. Or even if, when I say, okay, you go 1 3, either I can stop there because I cannot even go further. But even if, let's say I say, okay, traverse the remaining edges. So okay, I will go to 1 2. I'll place 1 2, then 2 1, obviously after that 2 1. But this is not following it. What went wrong? That's the thing. What went wrong? Coming back to our basics, what was actually happening from the start node? What actually start node is doing? Start node simply say, okay, some form of cycle, other form of cycle, and then some sort of straight line going towards the end. Right? Again, I'm not saying going towards the end, these will not go towards the end. Again, I showed you this can also go towards the end, but some sort of functionality like this, where I will have one outgoing edge, right? And then, okay, it will have some sort of arrangement. In that, you will easily see that if I do this cycle 1 2 2 1 1 2 2 1, you see 1 1, make sure that part 1 4 4 1 1 4 4 1 1 1. The only drawback was when I was actually visiting this, because this will say 1 3 1 3. Again, what if it could have 1 5 6 8, then obviously 1 3 3 5 5 6 6 8, ultimately it would be 6 8. So still 1 8 is remaining. So that is actually the culprit for me. This 1 8, what if this one could have happily attached with these because again these are working, so this one can attach with anyone, so he can attach with this one, but this one should have attached with any one of these ones happily. How to do it? We realized that when we did a simple pre-order traversal, as we were doing earlier, that okay, 1 2, I went to 1 2, then 2 1, then I did a 1 2 2 1, then 1 4 1 4, then 4 1, then 4 1, and then 1 3 1 3. It worked. But the moment I got unlucky and my DFS chose a different neighbor to go on to, I will be doing something like this. Okay, 1 2 1 2 2 1 2 1 1 3 1 3. I'm screwed up because next time, even if I go to 1 4, if I put a 1 4 here, that's not a good pattern, that's not a good arrangement. So, and even if let's say you try to start off from 1 3 itself, then again you're screwed up because next time you have to put a 1 2. How will you put it? So, okay, pre-order, you try. Let's try post order. That's the only option I have. So, okay, if I try post order, then again, obviously I'm saying try, but there's a very big strategy of why we are using post order. Let's see how. When I use a post order, which means what's happening, I start from 1, no matter wherever I'm going. Again, I'm saying no matter wherever I'm going, I will end at some point. So 1 2 1 3, either like this or 1 2 1 4 1 3. You see, I always ended up at 3, and even if okay, it's 1 3, I ended up at 3. So the fixed pattern which we can leverage here is always ending up at 3. So why not? Why not take this into consideration and reverse the thing? Maybe have a reverse pattern. So I will say, okay, 1 2 2 1 1 3, maybe like this. Okay, it traversed. So I will say that okay, do kind of a post order. Post order isn't like while coming back, make a pair. Why I'm doing it, you will see. But the fact here is that in the end, I'm touching that straight line segment. When I say straight line, I mean this segment, which is not a cycle segment. So when coming back, then I'm making the pair. Okay, 1 3. Then okay, coming back again. This is simple DFS when it comes back. Okay, 1 2 as a pair. 1 2, sorry. 1 2 as a pair. Then you will see, sorry, it is a 2 1 pair. Sorry. It is a 2 1 pair. 2 1 pair. Again, while coming back, I'm doing. And then next is 1 2 pair. You might say, Aryan, this is wrong. You lied to us. Technically not. So, okay, I made a 1 3. As you can see, 1 3, 2 1, and 1 2. 2 1 and 1 2. This is for this specific iteration when I have done the traversal, and while coming back, I made it. But the fact here is, while coming back, when I said I made it, I am always making sure that my shift portion is always in the end. Or I should say, this is the actually, again, when I say in the end, while traversing, it will always in the end. So for the post order, it will always be in the start. Then if I do any other traversal, which means for the remaining set of cycles which I had, or another edges which I have remaining, I will do a 1 4 4 1 coming on back. Okay, 4 1, and then after that attach a 1 4 1 4 attached. Okay, as you can see, 1 4 attached. Obviously this ultimately looks pretty bad. Why? Because you were actually putting up nodes while you were iterating from backwards, so you have to reverse it. If I reverse it, how will it look like? 4 comma 1 1 comma 4. Oh, that actually, no, 1 comma 4 4 comma 1, then 1 comma 2, then 2 comma 1, then 1 comma 3. You see what happened? This thing ultimately automatically came in the end, and this was only possible because you did the entire DFS while coming back onwards. You knew that this back onwards which you are coming, if it is the first time you are traversing, this back onwards coming will always be a straight path. If this is a straight path, if you reverse it, this will always come in the end portion, thus always attaching things correctly. So this is correct, because these were automatically cycles, so they will be correct. But this attaching was only possible because I did a post order traversal and then reversed it so as to put this again. When I say post order, so this will come in the first, but reversing it will make it in the end and thus making us the correct arrangement. And this is the corresponding answer that why you have to use in degree out degree. See, right now I never told you that you should be knowing Euler path, Euclidean path, this thing, Eulerian path, sorry. I never told you to know like this thing. You should never know it. People teach it, I don't know why, but you should know this thing may be called this. Like you traverse once, this is called this, but don't specifically jump onto something, okay, I should be knowing this concept and do that and then only I should do it. This is not how the problems should work. Now, ultimately, we know that this is what we have to do. Let's see the code. On the left side, I have Java. Right side, we have C++. For the folks taking anything, I'll explain Java, but the right exactly same is on C++. Now, here, firstly, I did one thing, very basic stuff. I simply made my graph. Now, the very interesting fact here is that you, when iterating on, for sure that you are doing a simple DFS, you have to not visit the same edge again. So you have to either mark things as visited, that's one way, or use some kind of data structure where you will be removing that edge, because see, this graph is something what you have made for yourself, not given the problem. So any edge addition or removal you can do to your graph data structure. So there is one very basic simple way is, as you are doing a DFS, simply keep on visiting, having a visited array where you will simply keep on visiting the corresponding edge. Or as you visit an edge, what an edge is for a node 1 in its adjacency list, we have node 2, node 3, node 4. This is what an edge represents from node 1 to 4, node 1 to 2 and node 1 to 3. As I visit this edge 1 to 2, I should just remove 2 from the adjacency list of 1. That's the ultimate maqsad. Now, while iterating, if you remove something, that's not possible if you use a unordered set or a hash set or something of that sort. So you can use either a stack or a DEQ, or to be very basic, you can use a visited array also. Cool. Let's see again. Someone's code I saw, they have used stack and I loved it. If I would have been, I would have used visited, but Leetcode editorial used DQ. This person used stack and I love the stack approach. So that's the reason I am here with the stack approach itself. So you made a graph again, rather than simply a list, you are having a simple stack, because this will help you to do concurrent operations. What I mean concurrent operations is that, as you simply know, that in a stack, while iterating on the stack, you can also remove things from the stack, right? That's the best part. So I have in degree map, I have out degree map. I iterated on all the pairs. I got the U and the corresponding, okay, let me show the corresponding code side by side. I got the corresponding U and the corresponding V. And then I made sure that in my corresponding graph, I am putting up this corresponding V for a corresponding U. Simply graph of U, push back your simple V, right? Out degree, in degree, just increase the corresponding hash by 1, which means out degree U plus plus, in degree of V plus plus. That's it. Again, this is how happens in Java. Then you have to find the start node. As I told you, start node is nothing but in your entire graph, you will check for any node whose out degree minus in degree difference is 1. That will be your start node. If not, then find any of the node in your entire graph. That will be your start node. Same thing, as you can see that I iterated on the entire graph and found out. If not, then give any of the node as a default node. Now let's have the answer and just do a simple DFS traversal to build the corresponding answer. Simple DFS traversal looks like that. Right now I got the corresponding stack. Simply this stack is nothing but the adjacency list, I should say the stack for the corresponding node. This is all the neighbors. This is all the neighbors which I have. I iterated on the stack itself until the stack is empty, which means trying for all the possible neighbors. When I visit a specific neighbor, I remove it from my stack and then I do a simple DFS. When coming back, I'm putting in my answer. When coming back, I'm putting in my answer. That's a very important fact. While coming back, so it's after DFS, which means while coming back. Now coming on back, I'll simply reverse it, because with that, the thing in the front will go in the end and will make me actually a correct traversal or arrangement. So I simply reversed it, and ultimately here this is the list. I have to return an integer array, so simply do a conversion, and ultimately here also I'm just simply doing the result and returning it. So that is your ultimately question. Cool. I hope you guys got it. I hope you guys liked it, and I hope you guys didn't feel the need to know something before solving a problem. Cool. Bye bye. Take care. And yeah, do join us on Discord and Telegram, and make sure to check out Twitter post recently. Bye bye.